Welcome to Dare to Know, interviews with quality and reliability thought leaders. I'm Tim Rogers, and today we have a very special interview recorded by Fred Schenkelberg. Fred's guest was Dr. Wayne Nelson, leading expert on analysis of reliability and accelerated test data. Formerly with General Electric Research and Development for 23 years, he now privately consults and teaches engineering applications of statistics for many companies, professional societies, and universities. For his outstanding contributions to reliability data analysis and accelerated testing, he was elected a Fellow of the IEEE, the American Society for Quality, and the American Statistical Association. The IEEE Reliability Division awarded Dr. Nelson with its prestigious Lifetime Achievement Award. Let's join Fred's interview with Dr. Wayne Nelson.
All right. So welcome to Dare to Know. This is Fred Schenkelberg, and I'm very proud to be sitting down with Wayne Nelson. Hey, Wayne.
Oh, it's good to see you, Fred. I'm glad we ran into each other here at Rams.
That's right. And we actually found a moment where it's a little quieter. But we were just talking, and we've known each other for quite a while.
Oh, I would say 20 years.
I think so. Yeah, and we were just catching up a little bit about travel, and it sounds like you've had some great times in New York and other parts of the world. But you made a comment, well, before we got started, that you're just a statistician, and there's a bunch of sessions going on with all these engineer types. Well, what was that about? Just a statistician.
I guess it's my way of saying I respect the knowledge that engineers have that I don't have. They are so intimately familiar with their products. It's the histories of the products, the failure mechanisms, all of the way the data, the development programs they use, the way they run their tests, how they handle the manufacture, how they handle quality control, how they handle service in the field. These are things I only know a little about. I'm just a statistician. I help them collect and analyze data on reliability of products.
That's right. And I'd say it's a little more than just help, Wayne. You've created some of the tools and techniques that are built into our tools, and it's the way we approach things.
Okay.
So you're being a little modest here.
Okay. I will admit to having a talent for solving problems that haven't been solved before, for inventing new methodology and models. I guess what it is I'm critical of the tools we have. In fact, you have this, I'll call it, small crusade against MTBF, which I agree with. It's been misused terribly, and it's rarely a useful concept. So I have to say, most people just repeat what they've read or what they've learned in school, and sometimes doing it badly. But I at least realize when something is not being done well, and I can invent a better way.
That's right. You come back with a solution, not just a complaint.
Yeah, a better solution than people are using currently.
That's right. Now, you've published, I want to hazard a guess, of hundreds, maybe 500 papers?
Oh, no. If you count company reports and client reports, maybe that many. But literature publications, about 130.
130.
Yeah.
Right, and it includes some of these new concepts and new solutions, but also a clear explanation of some of the things that are fundamental, the fundamental understanding of things.
Yeah, I think if I have any talent besides the ability to invent, it's the ability to see things simply and to explain them simply and clearly.
Well, do you remember when we were both attending one of the sessions here at Rams? It was a panel on standards, I think. They were talking about reliability standards. And I think I asked a question about MTBF and challenged them and why they're still using that. And you made the comment of it, the words we use matter. And so if we're using MTBF to convey reliability, why don't we actually use reliability? Or it was something along that line.
Or even if you're talking about repairable products or even life data, the failure rate or the repair rate.
Repair rate.
Yeah, that makes a lot more sense than MTBF. Yeah.
That's right.
Yeah.
But what stuck with me was that it was the words we use matter. And I remember we talked after that, and we were talking about, I was struggling with some people on and conveying what is confidence in statistical sampling. and you said, we have convincing evidence that the null hypothesis is not true.
Yes.
And you know, I've used that a number of times, and they say, oh, okay. You know, and if I use confidence, it's too tied up into the common language definition of that.
Yeah, that word I think is better omitted from statistical work because it's so misleading with non-statisticians. Statisticians really understand the meaning of confidence in terms of a confidence interval is the probability the interval covers what the value you want to cover with that interval.
That's right, the population
It's just a
parameter.
probability. There's no nice warm feeling that you have when you're confident. It's just a cold, clear probability that the interval covers the value you're interested in. That's provided that all your modeling and such is correct.
That's right. I
The
wanted to
probability is really greater or less than intended.
Well, in your book on accelerated testing, which is the first reliability book I picked up, it was, and that was 20 plus years ago, and I think we met at a small conference in Boston, and I was able to ask you a bunch of questions then. But one of the things that I don't see in a lot of books that was in yours was that you made the assumptions very, very clear. If you're going to use this distribution or say this approach, here's a list of assumptions that are built into this analysis. So if the data had to be normally distributed and you're assuming that or whatever the distribution is, and you made it stress that check it.
Yes, I was just going to say that very thing. A lot of people in many fields, especially engineering, and I've worked with engineers 50 years, so I'm pretty clear on how they think they've done the job when they say, I have assumed.
Right.
And then they never verify that the assumption or check that the assumption is a reasonable, plausible one for the situation. That always has to be done. I mean, you might say, well, I'm going to assume a Weibull distribution. That's not enough. You have to look at the Weibull plot, see if it's relatively straight, especially in the area you're interested in, the lower tail.
Right.
And then you can say, okay, the Weibull is a reasonable model to use here. You don't get away with just saying, I assume.
That's right. So, I mean, a visual piece is one check. And I had one professor tell me that you plotted on an 8.5 by 11 sheet of paper, the cumulative distribution function, put the data there in your regression line, and if it fits under a number 2 pencil, it's a pretty good fit. That was my favorite technique. I don't think I could write a paper and get it published on that technique. But
Again, everything is so conditional on the situation and the details of it. That pencil rule of thumb is probably good 10% of the time and not good 90% of the time.
Well, hopefully it was good enough for his class. That's what we ended up doing.
One of these rules of thumb that I have seen used and quoted since I was a freshman in chemistry, I was taking chemistry with Linus Pauling as a freshman. Just the basic course. Even he quoted the doubling rule for the Arrhenius, approximation to the Arrhenius. And I saw GE lose $1 billion because they believe the doubling rule for the effective temperature is correct. The doubling rule says for every 10 degrees centigrade, the failure rate or the life doubles or goes
in half, the other direction,
whichever way the temperature is going. And that isn't right. If you go to my accelerated testing book and put the doubling rule on any Arrhenius plot in my book, you'll see it doesn't follow the data.
That's right. That's right.
So I like the $1 billion loss because they looked at the lubricating fluid for a rotary compressor that was going to go into refrigerators.
Right.
And they went ahead and they ran their test at only one temperature.
And then they assumed
they used the doubling rule.
Energy?
They didn't even use an activation energy. They used the doubling rule.
Okay.
Yeah, the doubling rule and the Arrhenius curve are two different curves.
Right.
Yeah.
Yeah.
They're
overlap
not even
in a
close
certain
to
case.
each other.
Yeah.
Yes. So they just used the doubling rule to get to the design temperature. And I told them, well, you have to go back and collect data at least one other temperature to find out what the slope is in the Arrhenius plot.
Right, right.
And they didn't. They didn't. The trouble is, I was working with a sort of a junior statistician, not with the people who.
Well, that ties into, I think, my first comment about, just a statistician. You need to understand where the data set came from and what's the source of it and its nuances, and then how they're going to use the information. So that's where your interactions with all these engineers through the years is helping them inform how they make decisions. You just don't plug the numbers in a calculator and come out with a result. It goes somewhere. Somebody's going to use that. So if they would have, you use the principles you've put out in papers and other things, they would have checked assumptions. They would have,
Yes,
said, do we have enough?
like the doubling rule. In fact, you should never use the doubling rule unless you have nothing else. I mean,
right. And even then, I would
that's
say,
your last resort, not your first.
That's right.
Yeah.
Well, you've seen it, though, where people just don't have the samples, or we don't have the time, or we don't have the resources. What do you do in those circumstances?
Well, then you're an engineer. Statisticians don't do things like that. Engineers, with the pressures of getting the job done, they sometimes have to make decisions based on past experience or just a guess. Yeah, because they have to go forward and may not always give the best results, but
sometimes it works out well, and sometimes not so well.
Like the doubling rule for the refrigerated compressor oil, it just didn't work.
That's right. That's right. Now it's then you have a more recent book out. I think the last time I talked to you, it was fairly new. It was more on I want to say repairable data.
Yes, it's a book that was published by the American Statistical Association and SIAM, Society for Industrial and Applied Math. Mm-hmm. It does concern analysis of repair data and other types of recurrent events data. In order to sell the book to a wider audience, I included applications from medicine, like recurrences of cancer tumors,
right,
or recurrences of blood clots in patients, or falls of the elderly. I've also included some applications from marketing. I have some nice...
Would that apply like for repeat customers?
Repeat purchases on Amazon.com.
All right.
One of my associates from General Electric worked for them after leaving GE and provided me with some of those applications. And they were able to compare two marketing promotions.
Excellent.
Yeah, they've just randomly assigned a purchaser to one of the two promotions, and then follow the purchaser into the future to see which group of people made more repeat purchases. Right. And they found out there was a 10% difference in purchases between the
because
two
of the path they took.
Well, it's just you got promotion A or promotion B trying to sell you something.
Right, and it might be, I've heard of plenty of tests, and they would use a hypothesis test or a simple design of experiments to evaluate two sales pages. But you're adding the recurrent data of the repeat sales, which is a completely different question. And so a basic hypothesis test wouldn't necessarily treat that data very well.
You need special methodology for recurrent events data analysis, and it's really, you have to use random process theory. But in my little book, I use a very simple version of that. And my book is totally non-parametric, which is also nice.
It is. It's a little on the conservative side. I think it also makes it more accessible.
Yes, yes. The methodology is now being used more and more. As just a personal incident, I have had 4 episodes of blood clots in my legs. So, and that's dangerous. I was recommended a new medication to prevent clots, so I went to the web and got some of the studies and literature on the new medication. And they did one study with about 4,000 patients comparing the new medication with an old standard medication, and they didn't use all of the recurrences. They used only the time to first recurrence.
Okay.
And so they were throwing away data, and it's a multi-million-dollar study that carried out at many different clinics.
Right.
So I've written an article basically saying, use all the data. Yeah, for example, they lost 28% of the information using.
Wow. Yeah.
And when you're talking,
say
$10 million, you're throwing away 2.8 million.
That's right,
Yeah.
and you're trying to make as good a decision and study as you can. And
Yeah.
it's hard enough to get the data off.
And the reason is like any new methodology, it's been around only 25 years. It's not being taught in all the basic courses.
Right.
So people haven't learned it, and they don't know to use it, and they use whatever they've seen others use.
Right.
We're monkey see, monkey do.
We are, and oftentimes we don't have enough time to learn just what we need to know.
That's right, and maybe there's no way of knowing it's out there.
And that's, I mean, part of the podcast and the sites I'm doing is to try to raise awareness on some of this. So hopefully this will get people to look
in fact, going back to your crusade against MTBF, my book provides the methodology for handling recurrent events data where you don't use an MTBF. You actually look at the recurrence rate and how it changes over time.
That's right.
And it's non-parametric, so it doesn't have to be a constant recurrence
Well,
rate.
it eliminates a number of the assumptions that get us in trouble sometimes. We don't
Oh,
assume it's an
absolutely.
exponential.
Right.
And we just get rid of that altogether. Now, I was talking to somebody yesterday that's in a university program, mostly in reliability engineering and mechanical engineering. And I made a comment about, I have the statistics courses, the undergrad statistics courses gotten any better over time? And she said, we don't require that anymore.
This is for people in engineering and reliability.
In engineering and reliability. And
Well, as you know, there are certain fields in engineering where they are required to take statistics. Quality, manufacturing, and even chemical processes, because they have to do some regression modeling there.
Right.
But that's it. The mechanical engineering and electrical and other fields of engineering, statistics and reliability courses are not always required. They've got so much in their programs.
That's right.
that they've expanded them to 5 years in many schools,
some schools,
and
right.
still not have room to give good statistics background.
now, my opinion is that that's a mistake. In the real world, there's variability, and we need the language to at least ask the right
The
questions.
concepts, yes, right. I agree with you. I think people in engineering and many other fields should get a good basic statistics course taught by somebody who is doing applied work.
That's right. I think that's where some of the courses lose it, is they go into the theory and the background in...
Or they have mathematicians teaching the course instead of people who've come out of engineering, physics, or chemistry who suddenly discovered these statistical issues are very interesting.
Interesting and important.
Yes.
Well, are you looking for a teaching position? We could put the word out there.
No, I do give courses usually for clients in industry or
Right.
for professional societies. I've given courses for various societies, including the American Statistical Association, the American Society for Quality, the Mexican Institute for Statistics.
And you're fluent in Spanish, too.
Well, I wouldn't say fluent, but I manage just fine. I have a good accent, decent grammar, and if I don't know a word, I'll get it from somebody in the audience.
There you go.
Because many of them speak English.
So one of the questions I've had for many years is, I mean, you've published so much, and you've taught so much, and you've been involved with American Society for Quality, you've been involved with the American Statistical Association and a bunch of different
Also the IEEE. I may be the only statistician in IEEE who is a fellow.
That's true, that's true. And you've been recognized for your contributions over and over again.
Well, I
Why do you
have
do
to
that?
thank my clients. They provide the problems, the stimulation, and I respond to their needs.
Right.
Yeah, I don't sit in my office and think, what does the world need? My clients tell me what the world needs.
That's right.
Yeah,
And
I've been lucky to have good clients. And also I've been lucky to get the simple problems first and then the harder problems and still harder problems. So I've been able to think my way through all of that.
Okay.
Yeah, if I were posed with a very difficult, complex problem to start, it would be very difficult. But with the background I gradually accumulate, I'm able to handle these more advanced problems.
That's right.
Yeah.
But I asked Bill Maker how he got started in reliability, and he tells the story about you.
Oh, really?
And back at the GE, and I think at the Union campus or somewhere in upstate New York, you spent some time together. Well, how did you get into, because statistics is a very broad field, how did you it seems like you're focusing on the reliability statistics in general. How did you get into that realm?
That's an amusing story. As a kid, would go to family dinners and play poker. Age 10 or 11, I was at the table like all the rest. So when I took an algebra course, we had a book which had chapters on combinatorial probability, so you could figure out odds for cards and dice and all of that. So that sort of whetted my appetite. And
so it started with probability
Yes.
gambling. Isn't that how statistics actually, the probability got started? And
There was a lot, yes. Gambling
so
did stimulate some of the research, early probability development.
all right, so this is high school, junior high that you saw these courses, I'm sure, and then.
Well, I was. We didn't cover the combinatorial work in our algebra.
Oh, it was
book.
in the
I did
book.
it on my own.
Okay.
Yeah, because I was interested. And then in college at Caltech, I was in physics, partly because I had a lot of elective courses I could choose.
Right.
And I did end up taking a course in statistics. It was just a 10-week course out of a book by Freund. And it was a nice book. And so I had that little 10-week course background, went to work, went to graduate school for a year, and then went to work at Lockheed Burbank. Well, at that time, they were dealing with a problem with the Lockheed Electra. The wings were flexing as the plane would fly, and eventually parts in the wing would fatigue, and wing would fall off.
Well, that's not good.
They wanted to fix it.
Yeah, I can understand that.
They had about a half acre of engineers with the Marchant calculators, each given us a cell in the wing doing these calculations of the fatigue flexing.
Okay.
So they came to me with some data that they had collected on specimens, metal specimens, coupons, where they had runouts. You know, you put specimens at different stress levels, run them till their failure, but they stop at 10 to the 7th cycles typically.
Okay.
And they want to know, how do we get a fatigue curve? Life versus stress.
Right.
And they didn't know how to do it. I didn't know how to do it.
I was going to say.
I didn't know how to do it. So,
with a 10-week stats course.
But they came to me because I'd had the 10-week course.
That's great.
There is a Spanish proverb, en el valle de los ciegos un tuerto es el rey. Okay? In English, in the valley of the blind, a one-eyed man is king. I had one eye. 10 weeks worth.
Okay, all right.
So I started reading then on the job, you know, finding, I had to go to journals. I couldn't go to a textbook for analysis of life data. There was nothing available way back. This was 1960 when I was there at Lockheed. That's when the U-2 was shot down over Russia.
Right.
Gary Powers was captured.
Right.
And the guys around me, the engineers said, well, I worked on that plane.
Okay. But there was you're right, a lot of the techniques and stuff were really starting to be developed and explored. The quality world, it had SPC and Shewhart charts and process capability, so some statistics was there, but not the life data.
Engineers had quality control type statistics.
Right, but they didn't know the life
Nothing
data.
on life data. Of course, actuaries have been working with that kind of data for a long time.
Right.
And in fact, the first real modern type mortality data goes back to Edmund Halley. The fellow who discovered, the astronomer royal who discovered the periodicity of Halley's Comet.
That's right.
Yeah, I've been to London and he's in Westminster Abbey, among the other English immortals.
That's right.
And
yeah.
down there it says he was the astronomer and developed the fundamentals of life insurance. He came up with the first human mortality table based on real data.
Real data.
Up to that point, they had just imagined what the life distribution looked like based on
Anecdotal
common
evidence.
knowledge.
Right,
yeah.
right. So you're pulling information you can find from journals and so on, and
Yeah,
assuming you
and
found a
I found the
relationship there.
subject fascinating. It required maximum likelihood estimation in the few articles I could find, which then were just for the exponential life distribution.
Right, right.
That's all there was.
Well, I'll stay off the MTV.
A fellow named Epstein had done some work in the area.
Okay.
So when I went back to graduate school after taking the year off at Lockheed, I started taking statistics courses. Well, they didn't have any course that would deal with that kind of data, but I got more of the basic courses.
Picking up more of the analysis.
Design of experiments, regression analysis, and the usual things, even a little sampling.
Right.
I ended up finally deciding, after nearly having lined up everything for my PhD in physics, I had passed all the qualifying exams, the language exams in French and German, and I don't speak those anymore. I never did, really. And then I suddenly got religion. I decided that the statistics issues were more interesting. And challenging. There was a lot that was needed in terms of just how do you get a fatigue curve off of data with runouts, non-failures.
Right.
So I switched. After completing all of the course requirements, language requirements, preliminary exam requirements, I switched. Took me, I think it was 2 or 3 more years to take the courses in statistics and then to do my thesis work.
Right.
Yeah, it was a good experience because I had good professors, and when somebody came into the department and wanted consulting, they referred that person to me. So I worked with graduate students, I worked with faculty, and I got started in consulting, which is what I wanted to do anyhow.
Anyway.
I didn't want to go into academic work.
Right. And it sounded like you've been fascinated with the different types of problems people are facing. I mean, even that first one, that you were presented with a unique situation as far as they were concerned, and you invented a way to help them solve that. That sparked the passion, and so you were sidetracked a little bit by physics. I can understand that.
Well, I got into physics only because the first year at Caltech, everybody takes the same course. Second year, you go into a specialization, chemistry, physics, or engineering. And I chose physics only because I would have the most electives and could choose whatever courses I wanted. So it was almost a default. I had always been interested in science and technology, so that was as good a way to go as any.
So part of the audience is people that are getting started in their careers or managing engineers and teams and so on. What advice do you have for them as they're building their own careers?
Do what you love. I'm 80 years old today, and
today?
Back in August.
Oh, okay.
And I still love what I do. I work because I enjoy the work. The money is a byproduct. I'm not working for money. I'm working because I take pleasure in helping engineers make better productter.
Well, I can personally thank you for that attitude.
Well, I know you do that too.
Well, I try. Very much so. I had you as a role model because that my very first problem was the way you described it. It was very similar to my circumstances. We didn't have wings falling off of planes. It wasn't quite the same circumstance. Yet, where do I go? Where do I start? Now, I had your textbook. Right? So by the time I started, I had some really nice references.
There were no textbooks in my areas.
That's right.
At the time I started, so I had to invent a lot of what I ended up using, and there were literature articles too. People had been thinking about these things, and especially the actuarial statisticians. They work totally non-parametrically, and engineers prefer parametric models because for many applications where you're running a small test, you don't have enough data to do a non-parametric
meaningful one anyway.
analysis.
That's right.
Yeah.
But how about the invention part? And part of, I think you love that part of finding solutions and developing new programs is we've got a wonderful set of tools now and software packages and all these things that do stuff to us. Is that a benefit, or do you see that as a detriment?
Well, that's I'm sort of stuttering now because there's so many things to say. But let's start with the simple idea that when I'm teaching statistical methodology to engineers and even statisticians, I spend a lot of time on the model we're going to be using or fitting to data.
Right.
Its properties, how to interpret the numerical values of the parameters in the model. I mean, you should know what an activation of 0.3 electron volts really means in terms of the behavior of the product. So I want the people who attend my courses to understand what the models are and their properties and the meaning of everything in the model.
That's right.
Then I'm not concerned that they should understand what the computer package is doing internally to come up with the parameter estimates and the confidence intervals. That is something that the experts do for them.
Right.
You know, in the back of my chapters, I may show the computation, but in the front, I'm showing people, here's the model, here it's fitted to data, here's the interpretation of the fitted model, and here's the practical decision that's being made on the basis of all of this.
That's right.
That's right. So that's my approach to teaching people. Most people are really just going to be simple practitioners and use the tools that are already out there, the software that you mentioned. Now, talk about the quality of the software that has evolved over time. Bob Abernathy is a great friend, and he's done a lot for reliability for engineers. He's a great teacher. Great inspiration, but his original software was very primitive.
Well, we had difficult
through
tools.
people like myself, Bill Meeker, and many others, he has improved it to the point where it is now, and it's very sound, and it does most of the things that people need.
That's right.
Yeah. So he's been a very responsive person.
Well, the core of it, though, is, I think you said, is the understanding. It's just don't trust the numbers coming out. Ask the questions and understand the models you're using and the assumptions. I'll come back to that. I think I really stress that. Well, you know, Wayne, I really, really appreciate getting the microphone on you and chatting a little bit. I didn't know how you got it started in reliability. I'm sure that we could keep talking for probably another couple hours.
Yeah, I've had a lot of experience, I think, that would benefit your audience, insights that might be useful, but
we'll
maybe another interview some other time.
Yeah, I'll look forward to that. I'll make sure that happens.
Yeah.
So appreciate it, Wayne.
Fred, thank you for the opportunity to chat with you and share some of my experience with your audience.
All right. Well, thank you so much, Wayne.